Let's look now at another nice example of divide and conquer. This is the problem of finding the median. The input to the problem are n numbers, and these are in arbitrary order, so we assume the list is unsorted. And the input is given to us as this one-dimensional array, capital A. Our goal is to find the median of A. This is the middle element. When n is even, it's not exactly clear what we mean by the median. So for concreteness, let's define the median as the n over second ceiling, smallest element of A. So when n is odd, so n equals 2 times L plus 1 for some integer L, then in this case, the median is the L plus first, smallest. And there are exactly L, which are at most this median element, and there's at least L, which are at least this median element. It'll be useful for us to solve a more general problem. Instead of finding the median element, we want to find the k smallest, where k is an input given to us. More specifically, we're going to look at the following problem. We're given an unsorted list A, just as before, and we're also given an integer k, where k is between 1 and n, and our goal is to find the k smallest of A. So if we set k equal to n over 2, then that'll be the median. Now if A happens to be sorted, then it's easy to find the k smallest. We just output the kth element of the sorted list. So that gives us a very trivial algorithm for solving this problem. Given an arbitrary A, we simply sort A, and then we output the kth element of this sorted list. How long does this algorithm take? Well, merge sort, or several other algorithms, take order n log n time to sort A. So the total runtime of this algorithm will be order n log n. Now, is it possible to find the k smallest without first sorting A? That's what we're going to do now. And in fact, we'll find the k smallest in order n time instead of order n log n time. What we're going to do now is this very clever divide and conquer algorithm for finding the k smallest in order n time. This algorithm is due to Blum, Floyd, Pratt, Rivest, and Tarjan from 1973. The story is that they figured it out over lunch. Once you see the algorithm, and it's quite clever, it'll be quite impressive that they just figured this out just over one lunchtime. Now we're going to use divide and conquer to solve this kth smallest problem. And our algorithm, the basic approach, is going to be quite reminiscent of the quicksort algorithm. Let me remind you about the quicksort algorithm, and then we'll see the modifications for our approach. So we're looking at quicksort for sorting this unsorted list A. The first step in the quicksort algorithm is to choose a pivot, P. Then we partition the array A into 3 buckets based on their relation to the pivot, P. One bucket is for those elements strictly smaller than P, those equal to P, and those strictly bigger than P. We do one scan through the array A, and we put each element into one of these 3 buckets. Then we recursively run quicksort on the small elements and the big elements. We take the output, and our final output is the sorted list of the small elements, followed by the equal elements, followed by the big elements. Now recall, the whole challenge in quicksort is how to choose a good pivot. If we choose a terrible pivot, such as the smallest element or the largest element, then one of these 2 lists is going to be of size n minus 1. It's just going to go down by 1 element. And then the running time of our algorithm is going to be order n squared. So what's a good pivot for quicksort? It's the median, or something close to the median. For our problem, we're going to have the same challenge, how to choose a good pivot. That's going to be the main task. But quicksort ideally runs in order n log n time. We're aiming for an order n time algorithm. The key is that we don't have to recursively consider both A less than P and A bigger than P. We only have to recursively search in one of these 2 lists. Let's look at a specific example to see exactly what I mean for this third step. Let's look at the following example with an array of n numbers. And let's choose a specific pivot. Let's say the pivot is number 11. So we make these 3 buckets, those less than P, those equal to P, and those bigger than P. And we're going to take a scan through the array, and we're going to put each of these elements in one of these 3 buckets. 5 is smaller than the pivot. 2 is smaller than the pivot, and so on. 11 happens to appear twice, so it appears twice in this equal list. And these are the final buckets. Now, what is the k we're searching for? Depending on the k we're searching for, the k smallest will be in one of these 3 lists, and we can figure out where it resides based on how large these lists are in comparison to k. The smallest list is of size 4, so if k is at most 4, then we know the k smallest is in this list. So in this case, what we can do is we can recursively search for the k smallest in this list, and we can discard these 2 other lists. Now if k is 5 or 6, then what do we know? Then we know the k smallest is in this list, and then therefore it's equal to 11. So we don't need to recurse at all, we can just output 11. Finally, if k is bigger than 6, then what do we know? We know that the k smallest is in this list, so we don't search for the k smallest in this list because we discarded 6 elements from these lists. So we're going to search for the k minus 6 smallest in this list, a greater than p. Now the key is that we're always recursing on at most one list, either the small list or the big list, or in the middle case, we don't even have to recurse at all. Whereas quicksort has to recursively sort these two lists, less than p and bigger than p. In this case, we only have to recursively search in one of the two lists. Now let's go ahead and detail this for the general case, and let's write the pseudocode to make sure it's all clear. So we're given this unsorted list A, and we've given a parameter k, and we're trying to find the k smallest in A. Our first step, as in the quicksort algorithm, is to choose a pivot p. How exactly do we do that? Well, that's going to be our main task. We'll get back to that later. After we choose a pivot p, we partition A into 3 subarrays based on this pivot, the smaller elements, equal elements, and bigger elements. Now we're going to recursively search in one of these 3 lists based on k and the size of these lists. Now if this small list is, say, of size 4, and k is at most 4, then we know that the k smallest is in this small list. And in general, if k is at most the size of this list, then we can recursively search for the k smallest in this small list. So we run this algorithm recursively on this small list and search for the k smallest, and that's the output of our algorithm. In the middle case, k is bigger than the size of the small list, but it's not big enough that it resides in the big list. So therefore we know that the k smallest is in the middle list, and therefore the k smallest is exactly p. So we can just output p. No recursion needed in this case. Now in the final case, we know that the k smallest resides in the big list. So we're going to recursively search in the big list, but we're not going to search for the k smallest. We're going to have to shift it. So we know that we're discarding these many elements, the size of these 2 lists. So we're going to look for the k minus the size of this list minus the size of this list. So instead of searching for the k smallest in this large list, we're going to look for the k minus the size of the small list minus the size of the equal list. These are the elements that we're discarding. Now, this is the basic algorithm, but the key part is, how do we choose a pivot? And what constitutes a good pivot? What does it mean to be good? Let's first look at what a good pivot means. What's a pivot which would lead to an order n time algorithm? Now we're aiming for an order n running time, and we're trying to use divide and conquer. So let's look at the recurrences which yield an order n solution, and then this will give us some idea of the algorithm basic approach. Take a look at this recurrence. What does this recurrence solve to? T of n equals T of n over 2 plus order n. This recurrence solves to order n. How can we achieve a running time like this from the basic approach that we outlined on the previous slide? We have one subproblem which is of size at most n over 2. Well, in our previous approach, we either recurse on a less than p or a bigger than p. In order to achieve that the subproblem is of size at most n over 2, we need that the pivot p is the median. If the pivot is the median of the unsorted list, then we know that a less than p is at most n over 2, and a bigger than p is of size at most n over 2. And therefore, the running time of our algorithm will be exactly this, which solves to order n. Now the problem is that the whole problem that we're trying to solve originally was to try to find the median of this list. So if you give us a solution, then I can run for order n time and I can find the solution again. That's the punchline so far. But what if I don't actually have the median exactly? What if I have an approximate, a reasonable guess of the median? So suppose p is an approximate median. It's fairly close to the median, but it's not exactly the median. Let's just do a thought process. Let me look at this sorted array A. So I'm not actually sorting A, but I'm just thinking about it, this array A as being sorted. Then the median is lying right here in the middle. And here I have the smallest element, here I have the largest element. Let me look at the n over 4 smallest, and let me look at the 3n over 4 smallest. Suppose instead of giving you the median, I just give you something which is guaranteed to lie within this band. So it's at least the n over 4 smallest, and it's at most the 3n over 4 smallest. So it's not lying in either of these extremes, it's lying in this middle band. Suppose I can find a pivot which satisfies this. So it's going to lie in this band. What does that imply about the running time of my algorithm? How large are these subproblems going to be in the worst case? Well, in the worst case, maybe it lies right here. It's the 3n over 4 smallest. And then a less than p is going to be of size 3n over 4. Similarly, if it's n over 4 smallest, then a bigger than p is going to be of size 3n over 4. And in general, I know that the size of the subproblem is going to be at most 3n over 4. So my recurrence is going to satisfy this relation. Now the question is, what does this recurrence solve to? Turns out it still solves to order n. And in fact, I can relax it even more. I don't even need 3/4 here. I can look at the n over 100 smallest here, and then 0.99 n smallest over here. I just have to chop off a constant fraction on both sides. So what is my recurrence going to satisfy in this case, where it lies in this bigger bandit? So my pivot is at least the n over 100th smallest, and is at most the 99 over 100th smallest. In this case, the size of my subproblem is at most 0.99 n. So my recurrence satisfies this relation. What does this solve to? This also solves to order n. The key is, I need a constant here which is strictly less than 1. So I'm always chopping off a constant fraction of the nodes. Now we're going to define a good pivot as a pivot which lies in this middle band, between n over 4 and 3n over 4 smallest. That's going to give us this recurrence. But it's going to be important for our algorithm, actually, to remember this recurrence. We have some extra slack, so we're going to aim for a pivot which satisfies this relation. But there was going to be some extra slack, because I'm allowed to have any constant less than 1 here. And I'm going to have to utilize that extra slack in order to find the pivot, which is a good pivot. So in the end, our running time is going to satisfy a relation similar to this bottom recurrence. But our definition of what is a good pivot is lying in this middle band between n over 4 and 3n over 4th. We're going to say a particular pivot p is good if this pivot p is at least the n over 4 smallest and is at most the 3n over 4 smallest. What does that imply? That implies that the number of elements which are strictly less than this pivot is at most 3n over 4, and the number of elements strictly bigger than this pivot is at most 3n over 4. So if this is satisfied, then we say the pivot p is good. Our main task is to figure out how to find this good pivot p in order n time. If we can do that, then we're going to get a recurrence such as this. We're going to have a subproblem of size at most 3n over 4 because of this relation, and it's going to take us order n time to partition the array and to find the good pivot. And then we know that this recurrence solves to order n. So we'll be done. Question is, how can we find a good pivot in order n time? What's an easy scheme for finding a good pivot? Well, if I have no idea what to do, what should I do? I might as well act randomly. So in our case, what does that mean? That means let p be a random element of A. Choose a random element of A and set that to be the pivot p. Now what's the probability that p is a good pivot? Let's look at our thought experiment from before. So let's look at the sorted array A. We're not actually sorting A. We're just looking at the sorted version of A for the purposes of analyzing the probability that p is good. We have the median element, we have the n over 4 smallest, and we have the 3n over 4 smallest. What are our good pivots? Everybody in here is a good pivot. How many good pivots are there? There's exactly n over 2 good pivots. So what's the probability a random element is a good pivot? I can order this however I want. The fact is, exactly n over 2 of these elements are good pivots, and there's exactly n choices. So the probability a random element is a good pivot is the number of choices which lead to a good pivot divided by the total number of choices. The number of good pivots is n over 2, and the total number of choices is n. Simplifying this, we get 1/2. Exactly half the elements are good pivots. So no matter how you order this array A, we get a probability exactly a half of finding a good pivot. Now, given a proposed element as a pivot, how can I check whether it's a good pivot or not? Well, I can just spend order n time, and I can break partition A into those elements smaller, equal, or bigger than p. And if I keep track of their sizes as I go along, then I can easily check in order n time whether this proposed pivot p is good or not. What happens if it's a bad pivot? What should I do in that case? Well, I can rerun this experiment again. So I choose a new random element of A, and then I check whether it's a good pivot or not. If it's still a bad pivot, then I run the experiment again, and I keep going until I find a good pivot. Once I find a good pivot, I use it. In expectation, how many times am I going to have to repeat this experiment until I find a good pivot? This is like flipping a coin. If it ends up with tails, then I'll say that's a good pivot. If it ends up with heads, that's a bad pivot. I got probability exactly a half of finding a good pivot. So I got probability exactly a half of ending in tails. I keep flipping the coin until I get a tails. Once I get 1 tails, that's a good pivot, and I stop my experiment. How many times am I going to have to flip the coin until I get a tails? In expectation, twice. So it's going to take me order n expected time to find a good pivot. So the expected runtime of the whole algorithm is going to be order n. So this is a reasonable algorithm, but all I have guaranteed is that the expected runtime is order n. I want an algorithm whose guaranteed worst case runtime is order n. So how can we guarantee to find a good pivot in order n time? That's the task we're going to try to tackle now. Now our aim is to try to find a good pivot in order n time. And we want to do this in worst case order n time. What we just saw is an algorithm which finds it in order n expected time. Now if we can successfully find a good pivot in order n time, then the running time of our algorithm will satisfy the following relation. T of n is at most t of 3/4 n because it's a good pivot. So the subproblem would be of size at most 3/4 the original size, plus order n to find the good pivot, and order n to partition A into the 3 sets. Now this recurrence solves to order n. So the overall running time of our algorithm will be order n. Now we have a bit of slack in this recurrence. In particular, recall that instead of having 0.75 n over here, we could have had 0.99 n. We just need some constant less than 1. What we're going to do is we're going to use this extra slack as extra time to help us find a good pivot. So now we're going to spend, instead of just order n time to find a good pivot, we're going to spend order n time plus t of 0.2n. So we're going to design an algorithm with the following running time. T of n is at most t of 3/4 n. This is for the subproblem, once we find a good pivot, plus t of n over 5 plus order n. This t of n over 5 plus order n is going to be the time it's going to take us to find a good pivot. Now the key fact is that 3/4 plus 1/5 equals 0.95. It's strictly less than 1. So this recurrence solves to order n. So if we can find a good pivot in this amount of time, t of n over 5 plus order n, then we successfully have an order n time algorithm to find the median. Now what exactly are we going to utilize this t of n over 5 in order to find a good pivot? How are we going to utilize it? Well, we're going to choose a subset of A, which is of size n over 5, and then we're going to recursively run our median algorithm on this subset S. And we're going to set P, the pivot, to be the median of this subset S. The time it's going to take us to find the median of this subset S is going to be t of n over 5, since the subset S is of size n over 5. The question is, how do we choose this subset S? We need to choose this subset S so that it's a good representative sample of this entire array A. Let's take a look first at a naive choice of this set S, and then we'll see how that fails, and it'll give us some intuition about choosing a better choice for this subset S. What's a simple idea for choosing this subset S, which is of size n over 5? Well, perhaps the simplest idea is to let the subset S just be the first n over 5 elements of A. Then we're going to set our pivot to be the median of this subset S. How does this pivot perform? Is it a good pivot? It says pivot P a good pivot. No. Why not? Well, that would be too easy. Let's see why it fails. Let's see the scenario where this pivot P is not a good pivot. Well, suppose A was sorted. Well, in this case, actually, it's easy to find the median of A, so there's no reason we're running the whole algorithm. But suppose A is sorted, and then actually this is going to imply that this pivot P is a bad pivot. So if A is sorted, then what is S? S is going to be the first n over 5 elements of A, so it's the smallest elements of A. So S contains all of the n over 5 smallest elements of A. What is the median of these n over 5 smallest elements of A? The median of the n over 5 smallest elements is the n over 10th smallest element. So this pivot is the n over 10th smallest element of this list A. Well, if this is the n over 10th smallest element, then when we partition A into the small, equal, and big sets, the big set, all we can guarantee is that it's the most 9/10 n. And then if you go back to the running time of our algorithm, then we're going to have t of n is the most t of 9/10 n instead of 3/4 n. So this pivot P is not a good pivot because this large set is going to be too large in the worst case. So is there a better choice for this set S? Well, there's some hope because we chose this set S right now without looking at A at all. So can we look at A and do a little bit of computation and choose a better representative set S? So our goal is to choose a subset S which is a representative of the set A. What exactly do we mean by representative of the set A? We want that the median of this subset S is also a reasonable approximation to the median of the set A. Now the median of A has half the elements smaller than it and half the elements bigger than it. Now in order for the median of S to approximate this median, what we want is that each element of S is somehow has a similar flavor. So we want that each element of S has the following property. We want that there's a few elements of A that we can guarantee are at most X, and a few elements of A are at least X, so that these elements of A, which are represented by this element X. What exactly do we mean by few? Well, let's say it's 2. So we have at least 2 elements of A which are at most X, and at least 2 elements which are least X, and then if we add in X itself, then we got 5 elements here that we're considering. So we want to look at sets of 5 elements, and we want X to represent that set of 5 elements. So what we're going to do is we're going to break A into n over 5 groups of 5 elements each. Let's assume n is a power of 5 so that this can be done cleanly. Now, how are we going to get this subset S from this partition of A? Well, we're going to choose one representative from each group. So each group is going to choose, or we're going to choose, one representative, one element of this group, which is going to represent the group in the following sense. It's going to represent the group in the sense that at least 2 of the elements of this group are at most the chosen element, and at least 2 of the elements are at least the chosen element. Let's take a look at a particular group to see how we do this. Let's look at a group G consisting of the elements x1, x2, x3, x4, x5. Now, who do we want to choose from this group to represent this group in the sense that we talked about just before? Let's look at this group sorted. So let's sort the group and relabel it so that x1 is the most x2, is the most x3, and so on. Now, who are we going to choose to represent it in this sense? Well, we're going to choose the middle element, the median of this group. x3 has the desired property. At least 3 elements of G are at most x3, including x3 itself, and at least 3 elements, including x3 again, are at least x3. So if we take the median of each of these groups, then that gives us n over 5 elements, and each of those chosen elements in the subset S it represents a distinct group of 5 elements. So they each have this desired property. And this subset S is going to be a good representative sample of this entire array A. And that's it. Now we have the whole idea for finding a good pivot. We take this array A, we break it into n over 5 groups of 5 elements each. For each group, what we do is we sort it. How long does it take us to sort? Well, notice this group is of 5 elements. So sorting it takes order 1 time. It doesn't matter what algorithm we use. We can take an exponential time algorithm. Exponential in 5 is still order 1. So it takes us order 1 time to sort this group, and then we can take the median element of this group. And that's going to be the representative sample for this group. And we take the one median, the one representative sample from each group. That gives us n over 5 samples. And that gives us our subset S. And then we take the median of that subset S, recursively we find it. And that gives us the pivot that we use for A. And then we're going to prove that that pivot that we find, which is the median of this subset S, is a good pivot. So let's go ahead and detail the pseudocode for this algorithm, and then we'll go back and look at the claims that we're making about this pivot being a good pivot, and look at the running time of our algorithm. Now let's detail the pseudocode for our linear time median algorithm. The input to the algorithm is an unsorted array A of size n, and an integer k, where the integer k lies between 1 and little n. And the output of the algorithm is the kth smallest element of the array A. The first thing we need to do is find a good pivot. To do that, we break A into n over 5 groups of 5 elements each. Now to be precise, we should say the ceiling of n over 5 groups, because little n might not be a multiple of 5. But let's ignore floors and ceilings in this pseudocode. Let's denote these n over 5 groups as G1, G2, up to Gn over 5. Now how exactly do we break A into these n over 5 groups? Well, we can do it in any arbitrary way we like. The easiest way to do it is to take the first 5 elements of A, and put those into group 1, take the next 5 elements of A and put those in group G2, and so on. Now we have to choose one representative from each of these groups. Here's a for loop to go over the n over 5 groups. For the ith group, group GI, we want to find the median. To do that, we first sort this group. There's only 5 elements, so we can take any algorithm we like to sort it. And then we take the median of these 5 elements. And let's let mi denote the median of group GI. Now we want to look at these n over 5 medians which we found in step 2. Let's let capital S denote this set of n over 5 medians. Next, we want to find the median of this set S. This will be our pivot P. How do we find this pivot P? How do we find the median of this set? Well, we recursively call this same algorithm fast select on this subset S. Now S has n over 5 elements. We want to find its median. Therefore, we look for k equal to n over 10. The n over 10 smallest element of S is the median of this set S. And we store that in element P. Now we use P as our pivot. We partition the original set A into 3 sets. Those elements less than pivot P, those equal to the pivot P, and those bigger than the pivot P. This requires just one scan over the set A. Now we can use the quick select approach from before. Based on the sizes of these 3 sets, we either recursively search in the small set, the big set, or we simply output P. In particular, if the size of the small set is at least as large as k, then we know that the k smallest lies in this small set. So we recursively run this same fast select algorithm on the small set, looking for the k smallest. Now if k is big enough, in particular if k is bigger than the size of the small set plus the equal set, then we know the k smallest lies in this big set. So we recursively run fast select on the big set with this k scaled. So we set k equal to k minus the size of the small set and the size of the equal set, this part that we discarded. Finally, if neither of these 2 cases held, then we know that the k smallest lies in the equal set, and therefore we simply output P. Now these 3 cases are simply the same as we detailed before for the quick select algorithm. This completes the pseudocode for our algorithm. Now we can analyze its running time, assuming that this pivot P that we found is a good pivot, and then we'll go back and prove that this pivot P is guaranteed to be a good pivot. Now we're going to prove that this P that we chose is in fact a good pivot. Now let's assume this fact for now, and then let's look at the running time of this algorithm. Let's look at the running time step by step. The first step, breaking A into these n over 5 groups. How long does that take? Well, that just takes one swipe through the array A. So that takes order n time. Now we have to sort each group. How long does it take to sort one of these groups? Well, it's only 5 elements. So even if we use a super slow algorithm, let's say 5 factorial, we write down every permutation of these 5 elements and choose the one which is sorted. That's going to take us 5 factorial time, which is still order 1. So it takes us order 1 time per group, and there's order n groups, so the total time for this step is order n. Now we're going to run this same algorithm recursively on this subset S, which is of size n over 5. So how long does that take? That takes us t of n over 5, since this subset is of size n over 5. Now we partition A into these 3 subsets. That takes one swipe through the array A. That also takes order n time. And then finally we recurse on one of these smaller subproblems. How large are these subproblems? Well, since P is guaranteed to be a good pivot, we know that these subproblems are of size at most 3/4 n. So our running time satisfies the following recurrence. We have 3/4 n. We have n over 5 for finding this median of this subset S. And then plus we have order n for several of these steps. The key is that 3/4 plus 1/5 is 0.95, which is strictly less than 1. So this recurrence solves to order n, and we have an order n time algorithm. Now it remains to prove this claim, that P is a good pivot. Once we prove that P is a good pivot, we're all done with our algorithm. So we want to prove this claim that this P that we chose in our algorithm is a good pivot. How do we find this P? Well, we took these groups, G1 through Gn over 5, each with 5 elements each, and we took the median of each of these groups, and then we took the median of those medians. So we took these n over 5 medians of these groups, and then we recursively ran our algorithm to find the median of that subset of size n over 5, and that was our P. Now what I want to do is I want to sort these groups. And I want to sort them by their medians. So this has the smallest median, this has the largest median. I'm just relabeling the labels on the groups. Now this is just in the proof. The algorithm is staying the same. Just for the purposes of the proof, let's do the thought experiment where we relabel these groups. So we've relabeled these groups so that the first group has the smallest median and the last group has the largest median. Let's look at this set A pictorially, and let's look at it by groups. Here's the first group. It consists of 5 elements. Here's the second group, G2. It consists of 5 elements, and so on. And here's the last group, Gn over 5, which consists of 5 elements. Now it'll be important for us to consider the middle group, the group Gn over 10. Now let's sort each of these groups by smallest to largest. So this will be the smallest element of this group, and this will be the largest. And this will be the median. This will be the smallest, largest, median, and so on. So in every group, the middle element is the median. This is just for the picture purposes. Now what does our algorithm do? It takes the median of each of these groups. Who is the median? It's the middle element right now. So our subset S is going to consist of these medians, these n over 5 medians from each of the groups. And our pivot is the median of this subset S of medians. So it's the median of medians is our pivot P. Who is the pivot P in this picture? It's the middle element, which is exactly the median of this middle group. So this is P. Now I want to prove that P is a good pivot. So I want to first look at which elements are guaranteed to be at most P. Who do I know is at most P? Well, look at this subset S. P is the median of this subset. So I know that everybody earlier in this subset, these guys up to and including P itself, are guaranteed to be at most P. So that's n over 10 elements that are guaranteed to be at most P. Now, take this first element. Who's guaranteed to be at most it in its group, G1? Well, I assume this thing was sorted, at least for the picture purposes. So there's 2 elements, which are guaranteed to be smaller than it. Similarly, in the second group, there's 2 other elements which are guaranteed to be at most this median of this group. In every group, there's 2 elements which are guaranteed to be at most this median element. So what's my conclusion? My conclusion is that all of these elements in this box are guaranteed to be at most the pivot P, because their medians are at most this pivot P, and these elements are at most this median. What's the area of this box? How many elements are in here? Well, there's n over 10 groups, and in each group, I got 3 elements. So there's at least 3n over 10 elements which are guaranteed to be at most P. Now look at the partition of A into these subsets, smaller, equal, and bigger than P, and look at the subset consisting of those elements strictly bigger than the pivot P. So this excludes all of those elements which are at most P. So how large is this subset? Well, I've excluded at least 3n over 10. So therefore, the size of this is at most 7n over 10. Recall, what was my definition of a good pivot? I needed to guarantee that this set is at most 3/4 n. And I've shown that it's strictly smaller. It's at most 0.7 n. Okay, now let's look at the other side. Which elements are guaranteed to be at least P? Well, now I'm going to look at the other corner. All of these elements are guaranteed to be at least P. How many elements are here? Well, the same count. 3n over 10 are guaranteed to be here. So the number of elements that are at least P is at least 3n over 10, and therefore the number of elements which are strictly less than P is at most 7n over 10 similarly. And that proves that P is a good pivot. That completes the proof of the claim. Now a natural question is, why do we break in A into these groups of 5 elements each? Why did we choose 5? What would happen if we would have broken it into n over 3 groups of size 3 elements each? Or n over 7 groups of 7 elements each? This is a nice homework question to make sure you understand the analysis of this algorithm. So consider groups of size 3 each and 7 each, and look at the analysis of the algorithm. What is the recurrence in these cases where we break into groups of 3 or 7? Write down the recurrence and see whether that recurrence solves to order n or not. And that'll show you why we consider groups of size 5.